Good evening, guys, and welcome to EdSofta. My name is Bolu Atife, and I'm a staff of EdSofta. Um, Throughout the course of today, we've been doing the mini tutorials. We've been doing a mini tutorials called we've been doing a mini tutorial from us from EdSofta here, and today we've been talking about physics, different topics in physics. We talked about vectors, we talked about electricity, we talked about projectiles, we talked about um, radioactivity. Okay, so and finally we're ending today's class with we're ending today's class with fields. Yeah, we're ending today's class with fields. Okay, so now quickly before I go into before I go into fields, quickly I just want to introduce EdSofta. What is EdSofta? EdSofta is a tech company. We specialize in providing for solutions to help students to prepare for their exams. So we have two products out in the market right now: EdSofta UTME and EdSofta SSC. Okay, so this tutorial is powered by EdSofta. EdSofta is an app that prepares EdSofta UTME actually is an app that prepares students for JAMB UTME. It has past questions, study materials, and many other features that help students prepare for the exam. For these tutorials, we will be solving questions from the EdSofta app. And if you would like to download the EdSofta app, you can download it on Play Store. Just search EdSofta UTME. So you study right there on your Android phone. Or you can go to our website www.edsofta.com. It's here www.edsofta.com, and then when you get there, just click on downloads. Sorry, coming www.edsofta.com. Yes. So when you get there, just click on products. Actually, yes, products. Just click on. So sorry. Um, Yeah, www.edsofta.com. This is what it looks like. Edsofta.com. So you just simply go to the products page. Go to the products page, and then when you get to the products page, you just scroll down until you have to find. So this is Edsofta for UTME. So this is just a snippet of how the um, the app looks like. So we have a software for UTME, so you can get it on Play Store or you download it right there and then for your system. Okay, so now let's get into what we have for today. So we are talking on fields. Okay, we are talking on fields. Let me quickly open the yeah. We are talking on fields. There are three types of fields actually. We have gravitational field, we have electrical field, and then we have um, magnetic field. Electrical field, gravitational field, and we have magnetic fields. So first off, we're talking of gravitational fields. So now Newton came up with a law of gravitation that states that the force of attraction between two bodies of mass m1 and m2, yes, is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. It is directly proportional to the product of their masses and it is indirectly proportional to the square of the distance between them. So um, proportion, which basically is a very straightforward proportion, which is a very straightforward. So I'm just going to switch over to my board here, and so that we can. So according to Newton, right? According to Newton, I have that the force exacted and force exerted on between two masses is directly proportional to the product of their masses, which we are taking to be M1 and M2, and inversely proportional to what? The square of the distance between them. Inversely proportional to the square distance between them. And also recall that for us to remove the constant of proportionality, proportionality sign, we have to introduce a constant. So, and if we do that, what that leaves us is with this. If we do that, what I have here is force is equal to constant m1 m2 all over what r squared. Okay, so now what is our constant here? So the constant here happens to be a gravitational constant. We represent it to what? G. Gravitational constant, we represent it to G, and G most of the time is sorry, let me just confirm because it's a very big number. Let me just go confirm what G is. Let me just confirm what G is quickly. Okay, so G is our constant here. It's called what? A gravitational constant. It's called a gravitational constant. So instead of just writing K, all we have is what? G. And the constant is what? Is given as, which will always be given to you in the exam, is 6.7 times 10 raised power minus 11 Newton meter square kilogram per kilogram squared. Newton meter squared per kilogram squared. So that's the gravitational constant. That's gravitational constant, and that's the unit. It's as simple as that. Nothing added, nothing removed. It is as simple as that. Okay, so yeah. So another thing also to note Another thing also to note in gravitational field is so although we'll solve examples with this, but I just want us to quickly go through the slides. Then when we go through the slides, then we can now, when we are done with the slides, then we'll now start applying these formulas to solve um, questions. Okay, so now, so remember our weight, yeah, if you want to calculate somebody's weight, you do what? Mass times what? Times the You do what? Mass times acceleration due to gravity, right? Okay. So now look at it this way. Okay. Look at something here now. So now your weight is actually gravity acting on you, right? Your weight is actually gravity acting on you. Okay, good. Now, if your weight is gravity actually acting on you, then look at it this way. You have two bodies here. So this is the earth and this is you. This is earth and this is you. Now take this as so now to now calculate the force. So now the force that is acting between the both of you is what we would know as gravity pulling you towards the earth, right? Okay. So now if that is the force, then I can write something like this, that the force between I and the earth is, so this is my gravitational constant, times the mass of the earth times my own mass all over the distance between me and the earth. The distance between me and the earth. And also recall that we already have this formula which says that what? For my weight, remember weight, which is same thing as force, is equal to mass times acceleration to gravity. So that means I can also have it like this. So what does that tell us here? So if since I have both mass on the same side, I can cancel this out. What that tells us now is that acceleration due to gravity is calculated like this: gravitational constant times the mass of the Earth over the distance. That's just how you calculate. That is how we arrived at our acceleration due to gravity. Our acceleration due to gravity. So what we did here was, so the r here is what the distance between the, the distance between the Earth's surface and the core of the Earth, which gravity is actually pulling into, which happens to be what 6380 kilometers. Which I think 6,380 kilometers. Okay, so now once you put that and you multiply it with your gravitational constant, then once you have your gravitational constant times the mass of the Earth, so so you do mass of the Earth. Mass of the Earth is 5.98 times 10 power 24, and then when you do all these whole calculations, you will get your G as 9.80 meters per second. So that is how they came about the for acceleration due to gravity constant. Okay, yeah. So now another thing we would want to note here is the gravitational potential energy. Gravitational potential energy. So that's just pretty straightforward. What is just formula for that is just the force divided by what? The distance. The force divided, so gravitational potential, which can be given as U or V, any letter you like. So I'm going to use U, is given as what? The force over my distance. And I know that my force is what? Gm1 m2 over what? R squared. So if I multiply it by 1 over, sorry, it should be force times distance, not, sorry, is force times distance. Okay, so I know that I have gm1 m2 over what? R squared multiplied by r cancels this squared, so I'm left with what? Gm1 m2 all over what? R. Okay, so that is the formula for gravitation. So this is my formula for force. This is my formula for gravitational potential, and this is my force for acceleration due to gravity. Okay, so I think that covers everything we need to know on gravitational fields. Okay, so then another thing also to note is satellites, the motion of satellites, right? The motion of satellites. Okay, so now if you were to calculate the speed, hmm, calculate the speed of of a satellite orbiting around the Earth, it's just pretty simple. The formula for that is just the velocity is equals to the square root of velocity here is equal to the square root of gm over what? Over r. Gm m over r. That's just it. Okay, so I think that summarizes. Okay, so another thing I also want to say, yeah, another thing last thing I want to say is, okay, now there are two things actually that I want to say last. So Last thing I want to say is velocity due to gravity. Velocity due, sorry, not velocity, escape velocity. Sorry, not velocity due to gravity. Escape velocity. Escape velocity. Okay. So now my escape velocity is just simply the velocity required for me for you to move an object from the Earth's surface to infinity. This is the velocity required for you to move an object from the Earth's surface to infinity. And the formula is given as V is equals to square root of 2 GR. So you just need to keep these formulas in mind. There are a bunch of formulas in this field. You just need to keep these formulas in mind. Okay, so that's gravitational field for you. Okay, so another thing we want to talk on or touch on is sorry, let's just get back to our slide. Okay, so yes, Kepler's law. Okay, so now what's Kepler's law? There are three laws actually. Kepler's first law states that the path of the planet about the sun is elliptical in shape, with the center of the sun being located at one focus. Being located at one focus. So what does that mean actually? What that means is that I don't know if you've seen a diagram of the 9 planets. And if you've seen it, if you see if you've seen the diagram is just simply the diagram is just simply like the orbits around the sun, right? The orbits around the sun, if you see it, they are elliptical in shape, and everybody seems to be orbiting around the sun. So that's just what Kepler is just saying, that the path of planets around the sun is elliptical in shape, with the center of the sun being located at one focus. That's just it. Then Kepler's second law says that an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. What that just means is that let's give an example. Now we have months that are 30 days, we have months that are 31 days, we have months that are 28 days, 29 days. Okay, so what it's saying is, so now let's call the months that have 31 days a group one, group one, months that have 30 days group two, right? So now if you draw an imaginary line for when group one is in session or when group one is active, so when we are in 30, in the month that has 31 days, okay? So if you draw an imaginary line from the center of the circle to the center of the planet, sorry, center of the sun to the center of the planet, it will cover the same area that is covering. So we have okay, let's say 30 days at September, April, June, and November. September, April, June, and November. So for the 30 days, guys, so if you draw an imaginary line, it will cover the same area in September, April, November. That's just what Kepler is saying. If you draw an imaginary line, it will cover. So for equal intervals of time, it will sweep out equal areas. That's just what Kepler second law is saying. And the third law is saying that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So it's comparing multiple planets, different planets. So he's saying what he's saying here is that if I square the period of Mars and Earth, and I find the ratios, and I divide the both of them together, I will get the same thing as the cube of the distance of their distances between the sun and their planet and each of those planets. So if the distance between sun and Mars is 3 kilometers and distance between sun and Earth is, I don't know, 5 kilometers, So if I what he's just saying is if I the ratio of period is what amount it takes to complete what one cycle, the amount of time it takes to what complete what one cycle, abi. So he's saying that okay, if I calculate, if I raise that their period to power the power of two, and I calculate a ratio for that, it's going to be the same as the ratio of their distance of the distances between each of between those planets and sun. So you just need to have a basic understanding of Kepler's law, so that when they ask you theoretical questions, you would understand what is being said. Okay, so the next guy is what? Electric field. So Coulomb is the guy here, and Coulomb says that what the magnitude. So the thing is, they both look alike. Yeah, they both look alike. So Coulomb law states that the magnitude of the electric force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So same thing goes for same thing goes for so just the same way we did Coulomb's law, just the same way we did Coulomb's law. Sorry, what is his name? Newton's law for gravitation. Yeah, the same way we did Newton's law for gravitation. We'll do the same thing for Coulomb's law. We'll do the same thing for Coulomb's law. Okay, sorry, let me just bring up my board. Okay, so what does that mean? What does that tell us? So the force, so let's say, let me repeat what I just said earlier. So it says the force, the magnitude of electric force between 2 point charges, okay, is directly proportional to the product of the charges. It is directly proportional to the product of the charges. So if I write that mathematically, what that just means is F is directly proportional to the product of the charge. So if the charges are Q1 and and Q2, then what I have here is what is directly proportional to Q1, Q2. Okay, and it says is inversely proportional to the square of the distances between them. It is inversely proportional to the square of the distance between them. So as you can see, reminds us of this from gravitational field. So you have m1 m2 over what r squared. Okay, so Coulomb actually mimicked that, and he found that to actually to be true, and I was able to prove it. So that's why it became a law. And then, as usual, for us to remove the sign of proportionality, we introduce a constant. So we have Q1, Q2 over what? R squared. Okay? So, sorry, K, we're introducing a constant called K. Okay, so now in this case, our constant of proportionality is actually, so I don't know, for some reason, Coulomb's constant of proportionality is actually a very complicated one, which happens to be this 1 over 4 pi epsilon 0. So this his constant of proportionality. So that is his constant of 1 over 4 pi epsilon 0. Okay, so next question now is, sorry, just a moment. So what's epsilon 0? So epsilon 0 is actually a constant also. Epsilon 0 is a constant. So I'm just trying to find the exact number, because actually big number is somewhat of a big number. Okay, so constant K is actually 8.988 times 10 raised power 9. 8.988 times 10 raised power 9. So actually, so K is K. Then for epsilon zero, which you might not really need, but just for knowing sake, epsilon zero is 8.854 times 10 raised to the power 12 minus 12 actually. So epsilon zero is 8.854, just to confirm, 8 point what 854, 8.854 times 10 raised to the power minus 12. Okay, so that's what epsilon zero uh, that's what epsilon zero is. Okay, so okay, so that's Coulomb's law for you. So it somewhat mimics the whole idea of well, it mimics gravitational field in the sense that so we have something called electric field strength. Okay, now electric field strength or intensity at a point is defined as the force per coulomb in a small charged particle placed at a point which does not influence the field. So the formula is just what matters here. The formula is what matters here. So the formula for the electric field intensity, it will look like, so this is it. Formula for electric field intensity is just this. Um, so it's given as this is the force per unit charge. So remember, the force is what? So you can put this as KQ1 or K, yeah. So and the force is what? KQ1 Q2 all over what? R squared. So if you multiply by what? 1 over Q1 cancels out. So you have that E is equal to what? KQ over what? R squared. So that's electric field intensity for you. So another formula also that you need to remember is electric potential. Electric potential. And electric potential is defined as the work done per coulomb in moving a positive charge from infinity to a point. Work done. Remember, work done is also what force times distance. So what we are doing here is so the formula is just is you can derive formula. So I'm going to electric potential is going to be what V, and I'm going to say so this is what force time sorry is electric field intensity times distance. Electric field intensity times distance. And then we know that the electric so you know that electric field intensity is what K Q over what R squared. And distance can also be measured as what R. So R will cancel this square. So you now have what K Q over what R. That's what the electric potential. So this is formula that you should always what remember. Another thing you should always what remember. And then this also is another thing you should always what remember. Is another thing you should always what remember. Okay, so that is that for field. So okay, yeah. So the last thing we're going to talk about for today is capacitance. That's the last thing we're going to talk about. Okay, so a capacitor is just simply so capacitance is just simply the ability of a material to store charges. The ability of a material to store charges. The ability of a material to store charges. So that means a capacitor is actually a material or a device or a substance that can store a charge. So it's actually designed in the way it is designed actually is there are two conductors, yeah, two conductors, preferably of the same material. But they can I'll go crazy. And so two conductors. So these guys are conductors. And then we now have a what? A dielectric substance here in between. We have a dielectric substance here in between. We have a what? A dielectric substance in between those two. So this is where the charges are stored. So these guys conduct it, these guys conduct it, but they store it here. And the reason why you have to conduct it on both ends is so that if you to charge or to discharge, these conductors will be able to conduct the electrons. Okay, now the formula for capacitance is actually pretty straightforward. Formula for capacitance is actually pretty straightforward. Okay, so formula for capacitance is, and one thing also to note is that the capacitance is dependent on a couple of factors, right? It's dependent on how strong the dielectric substance is or dielectric material is. Then it's dependent on the, remember, the smaller the surface area, the bigger the resistance, the bigger the surface area, smaller the resistance, which we spoke earlier on correct electricity. So that means the bigger the surface area, the bigger the surface area, the bigger its ability to what? To store electricity, to store charges. The smaller it is, the harder it is. Then length also affects it. So to calculate the capacitance of a, sorry, I'm coming. Sorry, just give me a moment. Okay. Yeah, so calculate capacitance. Capacitance formula is given by, so this is it. So capacitance is given by, so I multiply by epsilon zero A over a distance. Oh, yeah, distance also plays a part. So it varies inversely as distance and varies proportionally as area. So the bigger the area, the bigger the ability to store charges. But so the closer the distance, the bigger the capacitance, but the further the distance, the smaller the what? Capacitance. So this is the formula for capacitance. Another formula for capacitance that we know is what? C equals to Q over what? V. That's another formula we have for capacitance. Okay. So another thing also to note is that capacitors capacitors can be arranged in what? Series and parallel. Capacitors can be arranged in what? In series and parallel. Capacitors can be arranged in series and parallel. Sorry. Okay. So so the thing to note here is, so capacitors, actually the way they are being solved, they are solved in the reverse of resistance. So for series, remember our earlier discussion where you said in series, you know that R total is equals to what? R1 plus R2, and parallel. Sorry. You have 1 over R total equals to what? 1 over R1 plus 1 over R2. Okay, so the inverse is what happens for what? For capacitors. So in series, sorry, let me use another color. Sorry. Okay, so series here would be um series would be capacitance, so sorry, 1 over C total, which is equal to 1 over C1 plus 1 over C2 plus 1 over C3, 1 over plus 1 over C 1 over Cn. Therefore, parallel, sorry, parallel. Okay, what I have is C2 same as what C1 plus C2 plus C3 plus Cn. That's just it. That's just it. So then another thing also to note is what energy stored in a capacitor. That's another thing you will be told to calculate what the energy stored in a capacitor. And there are multiple formulas because because of the way you can manipulate it. Okay, so the first formula we have is, so let me just get rid of all of this. Okay, so energy stored in a capacitor can be given as half CV squared, or can be given as half CV squared, or it can be given as half QV. It could be given as what? Half QV, or half Q squared over C. Half Q squared over C. These are the three formulas you can have. And the reason why I have to do multiple formulas is because remember this formula of Q equals to CV, or sorry, you know it as C equals to Q over V, which is the same thing. So you just continue substituting and substituting and substituting. That's why I have QV and have Q squared over C. So that is that. Okay, so um, also another thing to note also is that it's because it is the inverse. So remember, in resistors in series, the voltage changes but the current remains constant. But here, right, here the the voltage remains constant but the current what? The current varies. Okay, in series. But in parallel, the voltage remains constant and the current changes. But in this case, the current remains constant and the voltage what changes. So capacitance is when you're calculating in series or in parallel, is just the reverse of what is it called? Of resistance. Okay, so we that is all I have for you on that is all I have for you on fields. So electrical talked on electrical fields and talked on what gravitational fields. Okay, so next thing we're going to do is just go to solve a couple of questions on 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 fields, so electrical and the likes. Okay, so I want to use the EdSofta app to do that. Okay, so let me just boot up the EdSofta app. Uh, okay, so I've saved a couple of questions here. Okay, I've saved a couple of questions here. And this is a feature that comes with the EdSofta app, actually. So where you can save questions, you can save questions for you to that you can visit anytime you like. So it's a wonderful feature and that comes in handy. It sounds like this. Okay, so let's just jump right into it. So for gravitation, I'm coming. Let me see. Okay, so this is let's start with one that we are used to a bit. So it says two spheres of mass 5 kilograms and 10 kilograms are 0.3 meters apart. Calculate the force of attraction between them. G is equals to 6.67 times 10 raised per minus 11 Newton meter squared kilo per kilogram squared. Okay, pretty simple actually. So um, let me get my board ready. Where we can see some action. Okay, so for a brief moment, I will just leave the EdSofta app just to. Okay, so I have two masses, right? M1 and M2. M1 is what? M1 is 5 and M2 is 10. So M1 is 5 kilograms and M2 is what? 10 kilograms. Okay, remember G is what? 6.67 times 10 raised to power minus 11 Newton meter squared per kilogram squared. Okay, and the distance, which is R, is 0.3. So remember, the force of attraction between both of them is what? M1G, M1, M2 over what? R squared. So G is what? 6.67 times 10 raised to power minus 11 times 5 times 10 divided by what? 3 times 10 raised to power minus 1 is power what? 2. And that gives us 6.67 times 10 raised to power minus 11 times 5 times 10 all over what? 9 times 10 raised to power minus 2. So I'm just going to do some magic here. So I have all the 10 raised powers. I'm bringing them out. 10 raised to power minus 11 times 10 raised to power 1 divided by 10 raised to power minus 2. This is same thing as 10 raised to power 10 minus 10 actually divided by 10 raised to power minus 2. And when you bring this thing up, I have is 10 raised to power minus 10 plus 2. And that gives me what? 10 raised to power 8. So all the 10 raised powers are going to give me what? 10 raised to power 8. I know that. So the next thing now is to multiply 6.67 by 5. 5 is 5 times 7 times 5, 5 carry 3. 5 times 6, 30, that's 33. 5 times 6, 30, so that's 33.35. So I have what? 33.35 times 10 is power 8. Sorry, minus 8 divided by what? 9. So 9, can you see that I did all of this without using calculator? Do you understand? So simple manipulation here and there helps. So hopefully when we're having mass, we're going to be let's going to be teaching a whole tutorials on mass. Hopefully all these quick tips would be taught there. But this is just physics. So 9 here 1, 9 in 33 is that's uh, 27 remain 6 So that's 3 remainder 6, sorry, not 27. 3 remainder what? 6. 9 in 63 is what? In 7. Then 9 in 5. No. So 9 in 50 would be 5. So we'll roughly have 37 point something. So 37.05, sorry, times 10 raised power what? 8. Okay, so if I standardize that, what I have is 3.705 times 10 raised power. Okay, sorry, 3.7 times 10 raised power minus 8. Because remember, there's minus here already. Oh, sorry, this is supposed to be a mistake. This is a mistake. It should be, sorry, I didn't do this well. Okay, so 9 in 33 is what? Is 3. Remainder 6. 63, 7. In 5, remainder, then we have remainder 5, then in 50. So you have 3.705 times 10 raised to power 10 raised to power minus 8 and Newton meter, Newton meter squared. Okay, so that's just, I think no, it's Newton meter. Oh, sorry, it's force, just Newton. Sorry, force is just Newton. So Newton. So that is your answer. Okay, so very, very straightforward. Okay, so I think that's all the questions. That's question the only question. Time is fast spent. I would solve today. Okay, so any questions on on fields? Does anybody want me to solve a special question on fields for them? Do you have a question on fields? Or is there anything that you need explanation on concerning fields? Is there anything you need explanation on concerning fields? Anyone? Anyone? Any question? Does anybody have any question for me on fields? Nobody? Anyone? Anyone? Okay, so of we've come to the end of today's session on physics. Okay, so I wish every one of you success in your exams. I think JAMB starts on Saturday. So I wish every one of you success. Tomorrow we'll be holding um, another tutorial on another subject. So join us by 2 o'clock. Classes starts by 2 o'clock. Classes starts by 2 o'clock. So join us tomorrow by 2. So we're going to be treating another subject tomorrow. Okay. Thank you very much and have a good day.